Welcome. Today, we're going to dive into the fascinating world of polar function graphs. In this video, you will learn how to construct graphs of functions written in polar coordinates. You'll be able to understand the essential components of a polar function, like its input and output, and see how these relate to plotting a graph. By the end of this lesson, you will be able to construct polar graphs and visualize how a change in angle leads to a change in radius, drawing a curve. So, let's begin by reviewing the very basics of the polar coordinate system. First, let's understand how points are located in a polar system. Instead of using x and y coordinates, we use r and theta. The first component, r, represents the radial distance. This is the distance a point is from the central point, called the pole, which is usually the origin. The second component, theta, represents the angle. This is the angle measured from a reference ray, the polar axis, which corresponds to the positive x-axis. So, to plot a point r, theta, you start at the pole, rotate by the angle theta, and then move a distance r along that rotated line. Let's see this in action. Consider the point 2, 30 degrees. We find the ray for a 30-degree angle, and then we go out a distance of 2 units along that ray. And there is our point. It's a simple two-step process. Now, let's connect this to functions. In our familiar Cartesian system, we have y as a function of x. Here, we have r as a function of theta. A polar function is written in the form r equals f of theta. This means that for any input angle theta, there is a single output radius, r. The graph of this function consists of all the points, r, theta, that satisfy the equation. In other words, as we change our input angle theta, the radius r will change accordingly, and the collection of all these points will trace out our curve. It's a continuous process where every angle gives us a point on the curve. Let's make this more concrete with our first example. Our first example is a simple function, r equals 2. Let's find some points to understand its graph. Here we have r equals 2. Notice that theta is not in the equation. This means that no matter what angle theta we choose, the radius r is always 2. Let's make a small table of values. We can pick an angle, say 0 degrees. Since r equals 2, our point is 2, 0. At 90 degrees, r is still 2, so the point is 290 degrees. And at 180 and 270 degrees, r is still 2, giving us the points 2, 180 degrees, and 2, 270 degrees. Now, let's plot these. We mark the points 2, 0 degrees, 2, 90 degrees, 2, 180 degrees, and 2, 270 degrees. If we were to plot every single angle from 0 to 360 degrees, we would get a continuous curve where every point is exactly 2 units from the pole. The result, as you can see, is a circle. This shows a fundamental relationship. The equation r equals k, where k is a positive constant, always produces a circle of radius k, centered at the pole. What if the radius, r, depends on the angle theta? Let's try r equals cosine of theta. This time, as theta changes, r will change as well. To get an idea of the shape, let's create a table for values from 0 to pi, or 180 degrees. Remember, the cosine function's maximum value is 1 at theta equals 0, and its minimum value is -1 at theta equals pi. At theta equals 0, r is cosine of 0, which is 1, so we have the point 1, 0 degrees. At 30 degrees, r is 0.87. At 60 degrees, r is 0.5. At 90 degrees, r is cosine of 90, which is 0. And at 180 degrees, r is -1. This last point is tricky. Let's plot it. A negative r value means you go in the opposite direction of the angle. So for the point -1, 180 degrees, we find the 180-degree ray. But instead of moving left 1 unit, we move right 1 unit, along the 0-degree ray. Notice this point, 1, 0, is the same as our very first point. We've completed 1 full rotation of the graph. Let's connect all our points. Starting at 1, 0 degrees, as the angle increases to 90 degrees, the radius shrinks, hitting 0.5, 60 degrees, and eventually 0, 90 degrees. This forms the top half of a circle. Then, from 90 degrees to 180 degrees, r becomes negative, tracing out the bottom half of the circle. The resulting graph is a circle of diameter 1. So we've seen how a changing radius can create a completely different shape. The graph of r equals cosine of theta is a circle with its center on the x-axis. Let's explore another common shape, the cardioid. We'll graph r equals 1 minus sine of theta. The term cardioid comes from the Greek word cardia, meaning heart, and you'll see why in a moment. Let's build this graph piece by piece, focusing on how r changes as theta goes from 0 to 2 pi. It's helpful to remember the graph of the sine wave as we do this. The term 1 minus sine of theta shifts the sine wave up and flips it. As theta increases from 0 to 90 degrees, sine of theta increases from 0 to 1. So r, which is 1 minus sine of theta, decreases from 1 to 0. We start at the point 1, 0 degrees and move inward to the pole. Now, from 90 to 180 degrees, sine of theta decreases from 1 back to 0. This causes our radius r to increase from 0 back to 1. We start at the pole and move outward to the point 1, 180 degrees, completing the top left curve. We're halfway there. Let's complete the curve. From 180 to 270 degrees, sine of theta becomes negative, decreasing from 0 to negative 1. As r is 1 minus this negative number, it increases from 1 to 2. We start at 1, 180 degrees and move outward to our furthest point, 2, 270 degrees. This forms the smooth, rounded bottom of the heart. Finally, from 270 to 360 degrees, sine of theta increases from negative 1 to 0. This means r decreases from 2 back to 1. We connect our furthest point back to our starting point, 1, 0 degrees. And there it is, a cardioid, a heart-shaped curve generated by the function r equals 1 minus sine of theta. By tracing the changing radius for different angles, we can build the entire graph. Now, let's explore another shape, a limacon, which is French for snail. We'll graph r equals 1 plus 2 times cosine of theta. This one is interesting because the cosine term has a coefficient greater than 1. As theta goes from 0 to pi, cosine of theta goes from 1 to minus 1. At theta equals 0, r is 1 plus 2 times 1, which is 3. We start at our furthest point, 3, 0 degrees. As theta increases, cosine decreases and r shrinks. By 60 degrees, r is 2. At 90 degrees, r is 1. But what happens after 90 degrees? Cosine becomes negative. At 120 degrees, cosine of 120 is minus 0.5. So r is 1 plus 2 times minus 0.5, which is 0. We hit the pole at 0, 120 degrees. At 180 degrees, cosine of 180 is minus 1. So r is 1 plus 2 times minus 1, which is minus 1. This means we move in the opposite direction of 180 degrees, which is the 0-degree ray, and plot the point 1, 0 degrees. Connecting these points creates a loop. The curve traced out the outer part of the limacon from 3, 0 degrees to the pole, then traced out this inner loop. The loop is a result of the radius becoming negative. As we continue from pi to 2 pi, cosine will become negative then positive, completing the symmetric outer loop and taking us back to our starting point, 3, 0 degrees. This example highlights a key idea. The ratio of the coefficients, 1 over 2, is less than 1. This condition is what guarantees that our radius will become negative, producing an inner loop. So, we've explored how a changing radius creates curves. What if the radius is determined by a trig function with an angle multiplier? Let's graph the rose curve. R equals 3 sine of 2 theta. The 2 in 2 theta means the function completes its cycle twice as fast. A full cycle of sine is 360 degrees, so 360 divided by 2 gives 180 degrees. This implies the curve will repeat its pattern every 180 degrees. Let's track one loop. At 0 degrees, r is 0. As theta goes to 45 degrees, 2 theta goes to 90 degrees, and sine of 2 theta goes to 1. So r reaches its peak of 3. As theta goes to 90 degrees, r returns to 0. This gives us one petal or leaf of the rose. We've traced the leaf from the 0-degree line to the 90-degree line, with its tip on the 45-degree line. What happens next? From 90 to 180 degrees, sine of 2 theta is negative. This means r is negative. For instance, at 135 degrees, 2 theta is 270, sine is minus 1, so r is minus 3. But because r is negative, this point is at 315 degrees. This traces a leaf in the fourth quadrant. As we continue the full 360-degree rotation, the graph will repeat, tracing over itself. So, our rose has two petals. In general, a function of the form r equals a sine of n theta has two n petals if n is an even integer. We've now seen how trigonometric functions create complex and beautiful patterns in polar coordinates. So, we've practiced generating these amazing graphs by plotting points. Let's recap the essential knowledge we've gained today. First, we learned that the graph of a polar function, r equals f of theta, is the set of all input-output pairs, where an angle measure theta is the input and a radius r is the output. Second, we saw that changes in the input angle theta lead to changes in the output radius, r. These changes then dictate the distance from the origin and the angle from the positive x-axis, drawing a curve. We demonstrated this by constructing several graphs, like circles, cardioids, limazons, and roses, just by considering what happens to the radius as the angle sweeps around. You should now be able to construct a graph for a polar function and describe the roles of r and theta in doing so. Practice plotting these points, and you'll quickly become familiar with these shapes. Thank you for watching.